This lecture is intended to supplement the other lecture material related to homework 19, introducing capacitors. I want to walk through, kind of in my own way, how to think about capacitors. We've been discussing cell membranes or parallel plates as two ways of having a parallel amount of charge. So I want to imagine creating, I want to concentrate on the parallel plates, not the cell membrane in this case. So the diagram here on the left is two metal plates connected to a battery. The battery looks like the battery, and they're connected by wires. And the way when the wires are connected up, negative charge is placed on the upper plate, pushing negative charge off of the lower plate, and that negative charge then gets sucked into the battery. I should note here that, unfortunately, the convention is to talk about movement of positive charge, even though batteries move electrons, which have negative charge. So you'll see the arrows are in this moving clockwise, and that's because the convention is to talk about motion of positive charge, which by definition is the opposite direction of negative charge. Okay, anyways, when you connect a battery up to these two metal plates, it will push a certain amount of negative charge onto the top plate and suck a certain amount of negative charge off of the bottom plate. And the amount of charge it pulls off will depend on how strong the battery is. The standard way of describing batteries is describing the potential difference across the top and bottom of it, that is the voltage. So there are 9-volt batteries, 1.5 volt batteries, or whatever. When you connect the wires to of the battery to the parallel plates, negative charge and positive charge will develop until the potential difference across the plates is the same as what the battery provides. So we saw that the more charge you build up, the more voltage there will be, and the two are directly proportional to each other. And so one way to represent this idea is to say that the charge is proportional to the voltage difference across the plates, and that the constant of proportionality is called the capacitance of the parallel plates. And so you see that equation down there, where Q represents the positive charge on the lower plate, or the magnitude of the negative charge on the upper plate. Delta V represents the potential difference across the plates, or the potential difference across the battery. The two will be the same if you just give charge enough time to build up. And C then is the proportionality. Standard units, Q is in coulombs, V is in volts, and C is in farads. That's a new unit. Okay. So when we have two parallel plates, there's a relationship between the charge on each plate, the electric field that's present, the voltage difference, or the distance between the plates, and the voltage difference between them. So I want to lightly walk through these equations. The top equation here represents the electric field that exists between the plates. The second equation describes how, when the electric field is constant, there's a potential difference across the plates that we can calculate. If we substitute in the electric field value into this equation, we get the third equation, which describes the potential difference and the charge. We can rearrange this in a way that looks very similar to the equation on the last slide. That is, the charge and the potential difference are related to each other, and there's a constant of proportionality, the fraction E naught A over D. And so that constant of proportionality is called the capacitance. So I've copied down the equation from the last slide right here. And that tells us that when you have two parallel plates with an area A and they're separated by a distance D, their capacitance can be calculated using this equation. The epsilon naught, remember, is a constant. It's in the inside front cover of your textbook. It is 8.85 times 10 to the minus 12. Now, capacitors that we build in that we use in the lab, or when we apply this to things like a cell membrane, the situation is a little more complicated because material, or that equation that I just showed, applies only when there's air in between the positive and negative plate. In practice, there's material that's typically there. It's usually an insulator that doesn't let electricity flow across from the positive to the negative. Um, it's sometimes also called a dielectric, and that's because material, the molecules that make up the insulator, can weaken the electric field value, and that's a good thing because I'll, uh, when we weaken the electric field value, that increases the strength of the capacitor. So the diagram on the left here shows how the material in that's we can place in between two parallel plates, or that cell membranes use in the membrane material, create create an extra electric field that kind of counters the parallel plate electric field. Those are the two arrows that the two directions of the arrows that you see on the far left. The effect of that is to just make an overall net electric field that's weaker between the plates, because the insulating material is creating a counter electric field. The most convenient way to describe that mathematically is the top equation here, which uses, it's called kappa, it's a Greek letter version of K, that tells us how much the electric field gets weakened. So like, if a kappa value is 5, if kappa is equal to 5, it means that that insulating material makes the electric field 5 times weaker. And I'm going to just skip to the last equation here. When we have insulating material making the electric field 5 times weaker, that has the effect of making the capacitance, that capacitor, 5 times stronger. So if we have some sort of insulating material, we have an area of each plate, and we have a separation, we can use this last equation to calculate the capacitance of that material. Okay, I'll stop there.